going to be talking about polygons and motions, vectors. Before we do that, let's review. We just studied translation, reflection, rotation, and dilation. And what we have here is we want to take the triangle and rotate it 90 degrees clockwise. I'm going to draw the arrow, 90 degrees clockwise, show and work the new coordinates. Let's first establish the coordinates that we have. This coordinate right here we'll call A is at -8, -8. And then we have B is at -6, -4. And then C is -2, -6. We're going to be rotating this 90 degrees clockwise. It's nice to be able to just kind of draw a line and get a visual where you're going. We're going this way, 90 degrees. Now the trick to rotating 90 degrees is switch and flip. Switch the order and flip the sign. So step number 1, there's A, there's B, there's C, sub A. Step number 1 is you want to switch the order. Technically, that's going to be -8, -8, -4, comma, -6, and then -6, -2. That's switching the order. And then we're going to flip the signs. And now we're going to flip the signs because it's clockwise. We draw a clockwise arrow on the right and flip the sign. Clockwise arrow, flip the sign. Clockwise arrow, and flip the sign. Now we're going to plot these 3 new points. We have sub A at -8, +8. That's sub A. And sub B is at -4, +6. And sub C is at -6, +2. And we're going to draw a line here. And now it's nice to be able to check these. So if you look very closely, we're going to connect 2 points here. We're going to work with point B. So from here, the origin, we're rotating about the origin to our original B. We're going to draw a line. And then from the origin to sub B, you're going to draw another line. If you look very closely, you can see that that is a right angle, and if you sweep it, that is 90 degrees. So we have rotated 90 degrees clockwise. Now we're going to talk about vectors. Vectors. A vector is a graphic representation of a force which has both magnitude and direction. Magnitude would be how much strength and force that baseball player puts into throwing that ball, whether he's going to do a speed ball or whether he's throwing the ball to be bunted. That magnitude would be the amount of force he puts behind it. Direction would be which direction the ball would be tossed. Magnitude and direction. So a vector is something we use both in math and physics to represent something that has both an amount of force and direction. For example, imagine you're this baseball player here, baseball pitcher. And it says right here, we want to draw an arrow to represent the strength and direction of a baseball pitched to home plate. So if here's the pitcher, and he pitches to home plate, the direction is going to be the home plate, and he's going to toss it with enough strength to get it over home plate. So the direction would be towards home plate, and the strength, the force, would be enough force to put it over home plate. Now imagine someone with a beach ball stood on the mound at home plate. So now we have a beach ball. and we toss that beach ball towards first base. Well, the beach ball is not going to be thrown or carry as much force, so it would probably only go that far. It wouldn't even make it to first base. So in this case, because a baseball can be thrown with greater force, the vector representing it is longer. Because the beach ball carries less force, it's shorter, and we went towards first base, not home base, so it is also a different direction. So the blue arrow represents the baseball vector being pitched across home plate. The red arrow represents the beach ball vector of the ball being tossed towards home base, but not make it because it doesn't carry as much force. Those are vectors. Vectors have both force, which would be called magnitude, and direction. With a vector, the amount of force is called magnitude. Magnitude is represented by the length of a vector, and all vectors have both magnitude and direction. We're going to be doing four things with vectors. We're going to add vectors. We're going to multiply vectors. We're going to calculate the magnitude of the vector, which is its length. And then we're going to calculate the direction of the vector, which is its angle. So first we're going to do what's called geometric addition. Vectors. When you add vectors, physically, you have what's called a head and a tail. When you connect vectors, we're going to add this vector C and this vector D, head to tail, at point P. So step number one, when you add them, it doesn't matter which direction you go. We're going to start with 1 centimeter C. So you keep the same direction, and we're going to mechanically pull it down. And then we're going to connect it, that's the C vector, we're going to connect it to the D vector. And you have to connect vectors head to tail. There's your D vector. Now we could have gone this different direction. We could have started with the D vector this way and added it to the C vector this way. But you can see that we'd actually end up with the same. When you add vectors, when you connect the original head to tail, that is called the resultant vector. So this red vector is the resultant vector. That's how you add vectors mechanically. Now we're going to do vector addition and what's called scalar multiplication. We have the vector -1, -7, and then we have the vector 2, -6. So -1, -7 looks like this. -1, -7 means I go over 1, and then here I'm going to go down 7. 1, 2, 3, 4, 5, 6, 7. So our vector here, this would be vector A, would go like this. And we would call this -1, -7. And then here is vector B is +2, -6. So we're going to go over 2, 1, 2, down 1, 2, 3, 4, 5, 6. This would be vector B. Now let's do the addition, because that's what we just familiar. We're actually going to subtract and not add a minus b here. So to subtract a minus b, you simply take the x coordinates, and we're going to go a minus b, so that's going to be -1 minus 2, so we're going to have -3 is what's called our resultant vector. And then here we're going to do -7 minus 6. That's a double negative, so that's going to become positive. So our resultant vector is going to be -3, -1. So if we were to add these, it would be like this. -3, 1, 2, 3, -1. Or subtract these vectors, it would look like this. This would be -3, -1. This was a minus b. Now, if we want to do -3a, all we do is we take the coordinates of a, the vector points of a, and this is just like the distributive property. You multiply both by -3. The resultant vector in this case is going to be +3, +21. So that's how you add or subtract using addition or subtraction and multiply a vector. Now, magnitude of a vector. Magnitude of a vector. Magnitude, when you think of magnitude, you need to think of length. Magnitude is an issue of length of the vector 2, -2. So first we want to graph that vector 2, -2. So it is over 2 to the right, and then down 2. So this would be your resultant vector here. And that vector is 2, -2. Now if you look very carefully, you can see that what we've created technically is a right angle. So we have gone over 2 and down 2, and we want to find this length right here. You could see that technically what we have here is the hypotenuse of a right triangle. So we can use a squared plus b squared equals c squared. The way you represent this using vectors is we say the magnitude of a vector, and you use this double slash, equals square root your x coordinate plus your y coordinate underneath the square root sign. So in this case, the magnitude of our vector is going to be the square root of 2 squared plus -2 squared. And of course, this is 4 plus 4 square root. Our resultant for the magnitude is square root of 8. And that's going to be 2.8, which is approximately 2.8. So the magnitude of our vector in this case is a square root of 8, or 2.8. That's magnitude of a vector. So magnitude is the length of a vector. Direction is a concept, involves the angle of a vector from the y-axis. It is specifically always going to be from the y-axis. So in this case, we want to find the magnitude of the vector below, also find the measure in degrees of the acute angle formed by the vector and the y-axis. Do not round any intermediate computations. Okay, so step number 1, we want to find the length. That's magnitude. So let's double check. First off, this is 1, 2, 3, 4. 1, 2, 3, 4. So our vector components are going to be 4 and negative 4. So the magnitude of our vector is going to be the square root of 4 squared plus negative 4 squared. Of course, that's the square root of 16 plus 16. Square root of 32, which is approximately 5.7. We want to go to the second decimal place. That's 5.66. Now to find direction, we're going to be looking for this angle right here. This angle right here. Let's pull this out where we can see it. This angle is going to be theta. We're going to be using SOHCAHTOA. We have 4, we have negative 4. And we see here, this is going to be our opposite from theta. This is going to be our adjacent. So we're going to use inverse tangent, because that's TOA. Inverse tangent, opposite over adjacent, equals theta. So it's going to be inverse tan, negative 4 over positive 4 will give us theta. So negative 4 divided 4, of course, is negative 1. Inverse tangent, it says it's negative 45 degrees. Negative means it's downward. So you go from the y-axis and go downward, negative 45 degrees. So you're going to use inverse, sine, cosine, or tangent, depending on your given information, in order to find theta.